When a system ingests raw, unstructured information, it faces a wall of noise. The central objective of machine learning is to cut through that noise, detecting underlying mathematical patterns within the training data so it can build a reliable predictive model. But the algorithm itself is an isolated mathematical black box. It possesses computational power, but lacks contextual awareness. A system cannot simply consume data and autonomously learn. It requires a mechanism for evaluating its own performance. Without explicit feedback, it has no way to correct its initial assumptions or measure its own accuracy over time. That vital feedback mechanism is known as the supervisory signal. The presence, absence, or specific type of this signal dictates the entire architecture of the system being built. The landscape of machine learning is categorized precisely by this nature of training supervision. Designing a model is not a matter of selecting the most complex math. It requires leveraging the specific type of guidance available in the data environment. Supervised learning operates in an environment where the training data includes explicit labels. The system is provided with the exact desired solution from the start. The first primary application of this paradigm is classification, which focuses on sorting distinct inputs into defined categories. Looking at this diagram, we see how labels operate. Specific markers, like a check mark for safe or a block symbol for spam, are mathematically attached to individual email instances to train the sorting mechanism. This next chart demonstrates regression. Instead of sorting discrete categories, the algorithm maps distinct data points along a continuous curve to predict a numerical target value. By establishing this baseline pattern, the system can mathematically locate the missing numerical value for a new instance. Supervised models achieve high accuracy, but they are bottlenecked by an expensive requirement. Human operators must already know the answers for the entire training set. The reality of the modern web is different. It generates terabytes of continuous, massive datasets without any human categorization applied to them. When data is completely devoid of explicit labels, engineers deploy unsupervised learning architectures. This chart shows the starting state for an unsupervised algorithm. It faces a homogeneous, scattered arrangement of unclassified instances, lacking any defining markers to guide it. Without a supervisory signal to point to a correct answer, the system must autonomously deduce intrinsic topological structures within the data itself. Here we see clustering in action. The algorithm draws boundaries, separating those identical icons into 4 distinct spatial quadrants. The algorithm discovers that these groups mathematically exist based entirely on feature proximity. It separates them successfully, even though the system has no concept of what the groups represent in the real world. This visualization shows how unsupervised models parse highly complex datasets. A t-SNE scatter plot maps distinct semantic groupings, rendering high-dimensional relationships into formats human analysts can actually read. But high-dimensional data introduces processing bottlenecks. Datasets often contain redundant or highly correlated variables that slow down computation. To solve this, this diagram illustrates dimensionality reduction. The algorithm takes a dense 3-dimensional volume of data, flattens it to a 2D grid, and finally compresses it to a single line, mathematically simplifying the inputs without losing critical structural information. In feature extraction, a model evaluating automobiles might merge separate metrics for mileage and age into a single, highly accurate wear and tear variable. Beyond grouping and compressing, unsupervised architectures are vital for identifying data points that violate established mathematical norms. This chart maps anomaly detection. By establishing a dense cluster of normal training instances, the system immediately isolates the red cross, an instance spatially far removed from the baseline expectation. In industrial applications, that single isolated red cross represents a critical manufacturing defect or a highly irregular, fraudulent financial transaction. Advanced unsupervised learning operates as a strict data distillation process. It strips away noise to isolate core signals and extreme outliers. There is an extreme operational gap between the precision of a fully labeled dataset and the chaotic scale of entirely unlabeled data. Semi-supervised learning functions as a practical bridge across that divide. Looking at this matrix, we see the mechanics. A tiny fraction of explicitly labeled green triangles and yellow squares is deployed to propagate classifications across a massive sea of undefined blue circles. The unsupervised model groups similar data mathematically first. Then, a human operator steps in to label the entire verified cluster simultaneously, saving thousands of hours of manual entry. In other scenarios, external human labels are completely absent, but the raw data itself contains inherent internal geometry. This visual demonstrates self-supervised learning, where a labeled dataset is generated directly out of an unlabeled one. Engineers intentionally corrupt parts of the input data, like applying a large black mask to an image. The model is forced to calculate the surrounding geometry and recover the missing original information. These hybrid architectures bypass the human label bottleneck by maximizing the mathematical utility of the data's own existing structure. All previous architectures analyze static, historical datasets. The environment changes entirely when these algorithms face unpredictable, moving systems. This introduces reinforcement learning. The architecture shifts to an active agent, observing and interacting within a live environment. This diagram outlines the logic. There are no static labels to map. Learning only occurs through consequence. The robot agent interacts with the fire and immediately receives an explicit 50-point penalty. The feedback loop is continuous, driven entirely by these direct, measurable rewards and penalties. Over countless iterations, the agent mathematically updates its internal policy, actively altering its behavior to avoid negative outcomes. Reinforcement learning does not find patterns in history. It optimizes behavior for the future. The entire machine learning landscape sits on a single, continuous spectrum of supervision. On one end, supervised learning dominates. If you have a fully labeled dataset, your architecture is built to explicitly map inputs to known outputs. On the other end, unsupervised and self-supervised paradigms take over. Lacking explicit labels, the architecture must be engineered to autonomously discover internal topological structure. And separating itself from static datasets is the final dimension for dynamic optimization, where reinforcement agents learn through active interaction. The machine learning taxonomy is a precise toolkit, strictly defined by data constraints. An engineer's first and most critical task is never selecting the algorithm. It is identifying the exact nature of the supervisory signal in their environment.